Hello, my name is Colin Crowley, and this is my final presentation video for CS6460 Educational Technology. So I decided to create course content for a Quantum Computing 101 course for computer science master's students. I noticed that most computer science master's programs don't offer courses in quantum computing, and as such, there are not a lot of materials available that aid in the instruction of quantum computing and quantum information. So I thought it would be cool to create some. So I created basically 4 lessons that explain various basic topics in the field of quantum computing and quantum information. I also created a brief refresher course that just kind of explains or kind of reviews some basic topics such as like complex numbers and linear algebra that you would want to know going into a course on quantum computing. So I'm not actually going to teach the material in each of these lessons, but I will briefly explain what the lesson covers and sort of the key takeaways that I was hoping that students would get from looking at these slides. So in the first lesson, basically I'm explaining what a quantum computer even is, what makes it different from a classical computer. And the answer to that question is that they use qubits instead of bits. A qubit being, instead of a construct that can only take a value of 0 or 1, it can be 0 or 1 or a superposition of both. So in this lesson, I cover quantum gates, quantum circuits, and just basically how those work differently than their classical counterparts. In the second lesson, I start to explain some quantum algorithms. So basically I cover Deutsch's algorithm and the Deutsch-Jozsa algorithm. Deutsch's algorithm is noteworthy in that it is basically the simplest possible quantum algorithm you could imagine. It solves a problem in 1 step that a classical computer could only solve in 2. So it provides evidence that quantum computers may be fundamentally more powerful than classical computers. The Deutsch-Jozsa algorithm is able to solve a similar problem, but it's able to solve it exponentially faster than what we can currently do with the best known algorithms on a classical computer. In the third lesson, I talk about Grover's algorithm, which is a well-known quantum search algorithm that, unlike the algorithms from the previous lesson, would actually be of practical use to us were we to have usable quantum computers. And then in the fourth lesson, I finally get to efficient factoring, which is kind of the thing that most people, when they think of quantum computers, they think, oh, a quantum computer is able to do efficient factoring, which would break certain cryptographic schemes such as RSA that sort of depend on the fact that on a classical computer, factoring large numbers is not feasible computationally. So this is definitely one of the most technically challenging lessons because it involves a series of problem reductions that are not at all obvious. So it is a doozy of an algorithm and involves a fair amount of number theory, modular arithmetic, and math. I also created 2 course projects, not unlike the course projects that we have to complete as part of other OMSCS courses. I wanted students to actually get their hands on some code that would test their understanding of the concepts presented in the lessons. The first course project is basically to write some Java code that simulates Grover's algorithm. So I have a write-up that explains what is expected of the student, and then some Java code that they would be given that has some functions that are not implemented that they would be expected to implement. And then for the sake of the educational technology course, I also provided the solutions. So that's the first course project. In the second course project, I actually prepared a VM because I wanted it to revolve around QCL, which is actually a quantum computation language. So it is a language that that would actually run on a quantum computer. It's simulating quantum computation on a classical computer, but the language itself supports certain quantum programmatic constructs, like creating an array of qubits and running it through a quantum gate. So it is a language that looks a lot like C and supports a lot of classical constructs, such as declaring a classical variable, but you can write code, classical and quantum code together with it, which is basically what it would be like if you were actually writing an application in a quantum programming language that would run on a quantum computer. So here's that VM. So if you open a terminal, you can just type in QCL and get to the QCL interpreter, and so you can play around with the different QCL commands, just like you would with any other interpreter for a language that you were trying to learn. And then you can actually use it to execute a QCL file. So that's basically everything that I created for this quantum computing course. So basically 4 lessons and then 2 course projects. Feel free to come to this repository and poke around at the stuff that I made. Particularly, say, for example, looking at the first lesson, just going through each of the slides and seeing if it makes sense to you. It was my goal to try to add as much clarity to these topics as I could to sort of socialize and democratize this material. So looking at the slides and asking, is this actually making sense to me, or is it just as confusing as if I was reading a textbook on quantum computing, is feedback that would definitely be appreciated. Thanks so much for watching.